Who's taking the lecture notes today? Good. What tute are you in, George?
Yajin's tute. Monday.
Yanjin's. Yajin or Yanjin?
I can't say her name.
Yanjin. Yeah, Yanjin. Yeah. No, I was just checking that I hadn't been saying it wrong. On Monday. Yanjin's Monday tute. So who else is in that tute? Okay, it's just you two then. Now, please everyone take really detailed notes. Thurston and I were having a debate about, because in the budget for the course, it says how many hours you spend attending lectures and then how many hours you spend doing the wiki notes, the commentary. And it's 4 hours, you're supposed to be spending 4 hours doing the commentary. And Thurston was saying, oh yeah, but you should count some of the time they spend in the lecture as a wiki commentary time. And I'm saying, no, I think that's counted in the lecture time. And he's saying, but they're working twice as hard as normal. And I said, oh, I guess I could give them an hour's credit for that. But in any case, even whether you're supposed to be spending 3 hours or 4 hours, we do expect you to take really detailed notes and put up a really good set of wiki notes. And now last week's group was a mixed joy for me. They started straight away, and the people that did it put in a big effort, and it was really exciting, though I don't think they quite put in 3 hours each. But it was great to see. But more than half the class didn't do anything. And I really felt that left down the class. So at the end, the notes were quite sketchy. You know, my notes are crap, and this is supposed to fill in my notes, but it looked like it was just sort of less detailed than my notes even in some ways. So I was quite disappointed. They got a PC because I was really excited that it was on time, and some people did a really good job and started early. But as a tute, I didn't feel they pulled together. And so Rupert now, poor Rupert, has the poor job of going through working out who helped and who didn't. And those who did a good job get good citizenship marks, and those who did a bad job get asked to leave the country. So please, if maybe you could redeem yourself by helping out in some other way, but please, everyone taking notes this week, please do take really good notes, because the advantage of that is it means no one else has to take notes. It means you only have to take notes once in the whole course. So do your job well, and then everyone will benefit. Please, please, please. So I write a commentary on their commentary. I gave the tutors a D, even though I thought their notes were probably of HD quality, but they were late. But D was fantastic, but this one was just a PC. What's that? I thought it was minus 10% per day or 0. Yeah, it's like that. It's like minus 10% or 0. George, man. I'm an inconsistent. Tutor should get 0. Well, D's almost like a 0. It's like half a 0. I was going to give them 0, but then I halved it. And that's a D. You remember that time. Anyway, I said we weren't going to waste time this lecture, and already we've wasted 5 minutes. So let's not waste any more time, because we're in a rush. Look, they've already started their notes. Isn't that awesome? Well done, guys. Cool. Okay. Oh, you can't see that page. Let me just fix that page up. By the way, does everyone know what negative all means? In the ACLs, I think some people have got negative the wrong way around. Negative means if you match this, you don't get this. And I think some people don't want anyone to be able to do anything, which is all colon nothing, which means all can do nothing. But to make it really sure that everyone can do nothing, they put a minus in front. And I'm not sure what that means, but I think it means, what, if you're in all, you can't do nothing. I don't even know what it means. So please don't do that. Please read about ACLs to work out how they work. Let's just save that. So negative all right means no one can write to this page, but other than that, all the defaults apply. Lecture slides. Let's make them big. Grr. Okay, acceptance testing reps, please see me in the break between the lectures today. So I know, George, you're one. I saw the big list, there's lots of them. Well done, everyone. So if you're an acceptance testing rep, can you just come down and see me in the middle, and we'll just talk a little bit about what it all involves and have a chat. There's a strike on Thursday. We talked about that already. Lecture commentary on the wiki. We've talked about that already. Oh, we've done all the admin already, so we haven't wasted the time. Today is brought to you by the phrases is-a and has-a. We're talking about relationships. Now remember, an object-oriented program is, in a sense, looked down from above, a series of objects all just sitting there, sending messages to each other, interacting with each other, calling each other's functions. So from above, it looks like a whole lot of lumps or cells interacting. So our challenge as programmers is what parts of the program are going to be the cells, and what parts of the program are going to be I mean, what are the cells, essentially? What are the objects? What are we going to break the problem into? What are the components of the problem that are going to be the objects that communicate? And then, what is the relationship between these objects? Because it's all about relationships. And the sort of bread and butter vanilla relationships in object-oriented programming are ISA and HASA. So let's get them out of the way straight away. So when we're talking about a car, and we were thinking of having a car class, a class that modelled cars, what did we say when we were describing it? Remember we did it over here? A car, we were starting to chat about what a car was. And what did we say? Car has wheels. A car has an engine, has an accelerator, has a sunroof.
Conforms to the vehicle interface.
Conforms to the vehicle interface. A car also has, you can turn it on and you can turn it off, and you can push down on the pedals to go faster and push down on the pedal to go slower. So the car, essentially, when we talk about it, when we start to model it, we're really interested in what are the objects, what are their relationships with each other, and what functions do we want them to have? What responsibilities do we want them to have? So for the car example, we're saying, well, our objects are car, accelerator, wheels, engine, and the functions are things like go faster, go slower, turn engine on, turn engine off. And the relationships are things like a car has an engine. A car has a steering wheel. That's a HASA. If you wanted to record the fact that something is a HASA, that you've got a HASA relationship between the two objects, how would that probably be represented in your code to do a HASA? If I've got a car and it has a steering wheel, what do I type into my program? I give it a field. I give the car a field called steering wheel. And I literally say, the car has a steering wheel. It has a field that contains a steering wheel. So this is one way of modeling relationship between objects. And this leads to a really nice approach which we call delegation. So let's just go back to the task 2 that you've just done about modeling a safe combination lock. You could, we told you a combination lock has notches and pins and wheels and a bridge. What's it called, a bridge? A what? A fence. And it had a dial. And so you could have an object that's a fence and an object that's a dial and an object that's and it turns clockwise and anti-clockwise. So I guess you could have a clockwise object and an anti-clockwise object. But there's all these things that could be the objects, but the main and most obvious thing is you've certainly got a lock object, you've got a lock class, and you've also got a wheel class. Are those sort of the things you talk about the most, the things that seem to have the most work, the most responsibilities, the meatiest things. And the fence doesn't seem to really do much. Was it called a fence? Yes. Yeah, the fence doesn't seem to do much. You could have a fence object, but it doesn't seem to have to do much. So we'll come to that later on. We'll just look at the things that seem to do the most. Now, the two sort of main ways, I guess there are 3 approaches you could have done to that assignment. One is you could have done what we call the monolithic approach, which is like a C program. And you could have said, well, I'll just make a lock class, and I'll give it all these huge functions that the interface requires, and they'll be really huge, and it'll do all the work, and it'll look after everything. And if you think about it really hard, you'll probably get it right, and that's a traditional sort of program. But that's not an object-oriented program, and that hasn't got the advantage of an object-oriented program of modeling the problem. That's done a whole lot of rewriting and testing in your brain to make the code match the problem. But actually, the object-oriented approach, which we want to take, we don't want to sort of summarize the relationship between all the components into a function. We actually want to just have all the components and state what the relationships are and let the system have that behavior. So that leads to the second design, which is better than the first one, which is you would have a wheel object, a wheel class and a lock class, and you would say a lock has some wheels. How many?
Well, we're now on 3. But
Some people said 3, some people said 4. Okay, so lock has a wheel, lock has a front wheel, lock has a middle wheel, lock has a back wheel. So you've got 3 fields, middle, front, back. Okay, that's the HASA relationship. When I'm trying to run a course, it's really difficult, and I always am too optimistic about how long everything will take, and I get quite stressed, and there's not enough time in the day to devote to it. And then I end up being tired and not doing a good job, which is crazy because I'm so tired because I'm trying to do a good job. It's just crazy. And I run round and round in circles and I go really tired and sick. And my wife always says to me, and this year my boss has been saying to me, what do they say? Richard, you should take a break. No, because the job has to be done. Delegate. Well done. I can't believe I've forgotten your name. Chris. Yes. Chris. Chris Lamb. Hello. Well done, Chris. Yeah, delegate. You should delegate. I think, oh yeah, that's a good idea. So we employ all these tutors and they teach and they do all sorts of stuff and that's really cool. And we employ a subject admin and he does lots of the admin and that's really cool. We do all this sort of stuff and there's all these people doing stuff and I'm delegating to them and that's really neat. And this is what we want your code to be like. We could have a big enormous class that does everything and all this hard work, but everything is much more simplified if you store other things inside you, if they're hazards, and you delegate things to them. So instead of you having to keep track of where each wheel is, why don't you just have a wheel? Just put a wheel inside you. And don't you keep track of where the wheel is. You just say to the wheel, rotate 10 to the left, rotate 4 to the right, rotate 6 to the left. You just keep saying that. And then after a while, if you want to know where it is, what do? You ask it, where are you? You don't have to do all the work and look after it. Let the wheel look after itself. You delegate that work to the wheel. And now the wheel doesn't have such a big job to do. It doesn't seem so scary from his point of view. The wheel doesn't have to run the whole course. All it has to do is remember, do I turn left? Do I turn right? Do I turn left? Do I turn right? It's easy for the wheel to keep track of where it is. It's sort of silly for you to do it because that's the wheel's job. So that's what we call delegation. That's the hazard thing. And I have the car example here. Let's just look at the car code. Here's our car. It's got a field that we use to record whether the sunroof was open or not. That's not delegation. That was just a sort of shortcut we took. We decided not to have a sunroof, if you remember. But we have an engine, we have a speedometer, we have wheels, we have an accelerator, we have a brake. So we're delegating all these things to these guys. That's the hazard relationship between them. A car has of this, a car has of that, a car has of that. And for example, when we create a car, we create an engine at the same time and stick it inside. Interestingly, when we create the car, we don't seem to create a brake. Toyota. Okay. All right, so that's hazard. But now let's get up to ISA, because ISA is really what I want to talk about today. I must say I love hazard. Hazard is my favourite. I like hazard more than ISA, but ISA is what people get stuck with when they're doing object-oriented programming. They trip over all the time. There's lots of traps for young players if you get ISA wrong. So I think it's worth a little bit of time to think about it. And we will over the next week as well. Next week when we do inheritance, we'll be talking about ISA quite a lot. All right, I'm going to talk about subtyping and subclassing. And we talked about subtyping last week. We introduced it. Does anyone remember what a subtype means? The concept of subtyping. No. It wasn't in the notes either. So, might be hard to remember. But it's very important. It was probably the main thing we did last week. Subtyping emerges from this idea, this observation we made that in OO programming it's possible for an object to have more than one type. So there's this natural correspondence between a class and a type. If you're an object of a certain class, then you're an object of that type. Where a class is some sort of syntactical construct and a type has some sort of meaning to us as programmers outside the language. So, and there's a nice one-to-one correspondence. But we showed that in Java, or in any language, it's quite convenient if an object or an entity can have more than one type because it lets you do neat things. And we had the example of the car carrier. Do you remember the car transporter? It's convenient if it can carry more than just cars, if it can also carry taxis. So you create a new sort of object, you create taxis, even if they weren't envisaged when we first wrote the car carrier, and lo and behold, we can use all the existing code. We can load them into the car carrier. It's really nice like that. It would be terrible if we had to recall all car carriers to factories every time someone thought of a new car. Much better that the cars have a standard way of fitting together and sitting in things. So if we say something is really a car, is equivalent to a car, taxi is equivalent to a car, then it can fit in a car transporter. So that was that, and we did that with interfaces. Do you remember that? Okay. So it can be neat for an object to have more than one type for a range of reasons. One is it can be used by third objects, like for example the car transporter. They can be substituted for each other. Notice this only goes one way. So if you've got say for example you've got a librarian, and you've got the type human being. If you write something that a human being can do, or that needs human beings, can you give it a librarian? No. Don't be cruel. Don't be cruel. Librarians are awesome. You can. So that's sort of convenient. It's really nice if when we write code we can substitute objects for each other at runtime. That's very nice. Notice it doesn't go the other way though. If you write something that needs a librarian, can we give it an arbitrary human being? No. Okay. So there can be, sometimes there can be this sort of relationship between them, that they're substitutable but only one way. And the other thing is we can do everything at runtime. It's not a compile time or design time problem. So when you create new things, you don't have to go through and change all your code. You don't, when you think of a new sort of car, when you design a hybrid vehicle, you don't have to go through to the car transporter and add a few more classes to a case statement. If it's a this, do that. If it's a this, do that. The car transporter can just do it. Okay. So there are lots of reasons. There are lots of other reasons too, but they're just some reasons why it's quite convenient to allow one object to have multiple types. So object-oriented languages have this thing called subtyping. Let's have a look. Well, actually, not just object-oriented languages, but it's pretty important in object-oriented languages. So that's probably the most. Oh, well, actually, it's pretty important in most languages. It's a really neat idea. It supports something neat called polymorphism, which we will talk more about later on. All right, subtyping. What's subtyping mean? Well, it's washed out, isn't it? Let me say, let's start by talking so there's two terms, subtyping and subclassing. And as you've seen, a class is sort of similar to a type, but a type is more an abstract concept that we have in our head, and a class is more a syntactical construct. And we've seen that one class can have multiple types. Okay, so in Java, when we talk about something having a subclass, so for example, we have humans and we have librarians, we'd say librarians are a subclass of humans if all the functions that exist for humans also exist in librarians. So anyway you could use a human, you could also use a librarian. It may well be you can do extra things with a librarian that you can't do with a normal human, whether just a random human. You can't expect out of every human. But if all the public functions of humans are also supported by librarians, then we could say that it was a subclass of it. This sort of subclassing is trying to capture a relationship called the is-a relationship, which is a librarian is a human. So if something is a something else, then we can say they have this relationship between them. And just because, and you can see is a isn't necessarily a reciprocal relationship, symmetrical relationship. Just because A is a B doesn't mean that B is an A. Okay, now the different ways of arranging subclassing. In Java, I'm being coy because I don't want to talk about inheritance yet. Java has a mechanism called inheritance that sets up a subclassing hierarchy. And what it looks like, without going into the details of how it's implemented or why, is that you have a series of objects, classes, and they're arranged in a tree. So you could have librarians and you could have teachers. And you could have public servants. And you could have, what else? Engineers. And you could have programmers, and so on and so on. And then librarians, well, what sorts of librarians could you have? Oh no, let's not get into librarians that are teachers. That's a natural question to ask. And this is going to be the problem with this hierarchy. It's going to be a loop-free hierarchy at the moment. It's just going to be a tree. And we are going to have problems because we are going to have people that are both teachers and librarians. We're going to have people, I can't believe it's possible, that are teachers and programmers at the same time. We're going to have these crazy classes, and we're going to have crazy relationships between classes, and we're going to have to deal with them. So, but let's not worry about that at the moment. Oh, well, no, actually we can. How would we do that in Java? It's like having a vehicle that's both a public transport vehicle and a car-like vehicle. How would we record that? Yeah, we'd use an interface. Yeah. We could use interfaces to say that something was of this and of this. All right, maybe you've got librarians that just love the Dewey system, and you've got librarians that love the Library of Congress system. And then you've got, what other sorts of librarians do you have? Librarians that are rock stars. And it's not a very good example, but maybe with teachers, you've got university teachers and high school teachers and primary school teachers, and then maybe the high school teachers, you've got math teachers and French teachers and, okay. Now, if you need a teacher, you could substitute any of these. If you need a high school teacher, you could substitute any of these. If you need a maths teacher, though, you can only use that one. So this is a relationship. It's a hierarchical relationship between classes. And it gives us our substitution that we want. Essentially, it happens because what we're saying is for this hierarchy to hold, anything down here has to have all the functions that this guy has, plus it can have some more if you want. So anything that expects all these functions can use this object because it has all those functions. And we can arrange all our classes into a tree like that, and this is called subclassing. So we would say a library is a subclass of humans, and a teacher is a subclass of humans, and a school teacher is a subclass of teachers, and so on. And simultaneously, a school teacher is a subclass of humans as well. Okay? Does that make sense? It's a hierarchical model. Now, not everything can be captured in a hierarchical model, but a lot of things can, so it's a convenient model for the language to support, and it supports it very nicely indeed. Let me just talk about military secrets. In the army, which is a hierarchical organization, the idea is you trust people increasingly as you go up higher and higher. So you could say, you are cleared, Shogun, you're cleared for confidential documents. He can read normal documents, but he can also read confidential documents. And you, I've forgotten your name? Amy. Amy, you are cleared for secret documents. You can read secret documents, you can also read confidential documents, and you can just read normal documents. And you, who is?
Oh, Hilario. Hilario.
Hilario. That's an excellent name. Well done. Hilario. I really like names with O in them because O is really important in this course. You could be cleared for top secret. So you can read top secret documents, confidential documents, and so on. And essentially, this is how information is organized securely in the military. It's by something, it's called multi-layered security. And there's all sorts of complicated, elaborate models describing this and maths about it and so on and so on. But you can see probably the problem that the person at the top who's cleared for everything has to be very, very trusted. And if they're an idiot or something like that, for example, normally that would be what, the president, I guess. If the person at the top's your stuff. But essentially it lets you capture that relationship and it lets you manage data and sort it out and so on. And it's very, very similar to this. But what they found during the Second World War was that model didn't work very well. It worked well for lots of things, but sometimes you had a secret and you didn't actually want to tell everyone about it. Like, for example, my favorite secret is the Enigma machine secret, because the fact that the Allies had cracked the Enigma machine and could read the German Enigma traffic was such an important secret. Churchill reckoned it was probably the most important secret of the war. He didn't want anyone to know about it. So that was what it was secured by another system of secrets called multilateral security. Multilateral security, or sometimes called code word security. So they'd say, knowing about the Enigma machine, knowing that we've cracked it, is magic. It's called magic. That's the keyword. It's a magic keyword. And you could be cleared for top secret, but you might not be cleared for magic. And you might only be cleared for confidential, because you might be the clerk in the room at Bletchley Park, but you have to know that we've done it, because you see all, so you're cleared for magic. So the idea was, in addition to their hierarchical model, they had a sort of ad hoc model, where anyone cleared for magic knew it all, but if you're not cleared for magic, you couldn't do it. You couldn't see it. And in fact, this was actually a real problem for the Brits after the war, because one of the rules, Churchill was so paranoid that people would find out about it, that he said no one with magic clearance is ever allowed to leave the country, or go to Germany, or go anywhere they might be captured. So after the war, when everyone was sweeping through Germany doing the tidy up, all the top cryptographic people in Britain, because of this rule, weren't allowed to leave Britain. It took a little while for the rule to be rescinded. And all the really good cryptographers in the Russian and American army actually went into Germany and stole all the German cryptographic stuff and all the German ciphers and all the German transcripts of what the armies had been saying. And the Brits missed out on all. It was very sad. Okay, but you get this idea. Now, code word clearance, this ad hoc thing, is like inheriting from an interface. So, car. You implement car. You implement car, you implement car. It's like saying you implement magic, you implement magic, you implement magic. You guys are now all allowed to be used instead of cars. And the other model, the hierarchical model, is I just get it sort of mechanically, automatically. If you're a science teacher, then by virtue of the hierarchy which Java knows, you happen to also be a human. Does that make sense? Okay, so there are two different sets. Now, Okay, let's ignore all that. Now I want to talk about subtyping. So you know about this notion of subclassing. Subclassing is essentially saying the classes share a common interface, or the public functions of the subclass has all the public functions of the parent, so you can use it instead of the parent. It's all about this sort of substitution thing. But it turns out that subclassing is subtly different to subtyping. Well, let's think about that. Subtyping is, it's safe to use you instead of you. It's safe to use a taxi instead of a car in your program because they're the same type, so it makes sense. It's a sort of conceptual idea. Subclassing is, it's legal to use you instead of you because you have the same interface functions. So it's a sort of syntactical construct. Can you think of an example where you could set up two classes, one of which is a subclass of the other, one of which implements all the functions that the other one implements, but you couldn't use it instead of the other one? Yes?
Like a queue is a type of list, but you couldn't actually use a queue as a list if you wanted all the functions in a list.
Okay, let's think. A queue is a type of list. Oh, no, but is it? No, it has less functions in the list. If the queue was to be a subclass of list, it would have to support all the list functions and more, and the queue functions. So could you say a list is a subclass of queue? No, they have an uneasy relationship between them. I don't think one's a sub of the other. You might be able to set up an ad hoc relationship between them, but they haven't got a hierarchical one. Yeah. But that was a good shot. Yeah.
Square and rectangle.
Oh, the square and rectangle is a famous one. Well done. Okay. Will you tell us?
Well, basically, the rectangle is a subclass of square.
Well, let's ask everyone. Think about it, guys. Think about it. Let everyone think about it. The famous example is square, rectangle, or circle ellipse, but I've got a class called square. I don't know why I wrote an 8 there. SQ. And I've got a class called rectangle. And square objects have certain functions and rectangle objects have certain functions. Do you expect that one of them will be a subclass of the other? Which? Square will be a subclass of rectangle. Now why? Tell me why. Because what? A square fits in a rectangle. This is like, I actually do object-oriented programming with those, you know, those little containers you get with the holes cut out. And yeah, I think that is a brilliant model, a way of doing inheritance. Let's see, but tell us more precisely.
Has two parallel.
Yeah, well, let's look at the is-a. Is it the is-a relationship? Could you say a square is a rectangle? Yes. Ah, okay. Well, it looks like they should have a subtyping thing going on then. Will they have the same functions? Will it be not the same functions? Will it be the case that the square has all the rectangle functions, but it might have some extra ones? Yes and no. Let's say there's someone saying yes. You're both right. Who said yes? They're both right. No one's going to be wrong answering this. Why is a square an example of a rectangle? What are the functions that they'll have in common? Width, height, area. There's no reason you can't say, you're presumably saying get width? Oh, yeah. Yep. Get width, get height, get area, get width, get height, get area. And maybe you've also got something like get perimeter, and maybe you've got something called draw me, where you draw me on some sort of graphic object. You know, you give it some object and it draws you on it. And there's no reason the square couldn't have all those things. So it sort of looks like they're a subclass. But what's the problem? Someone that said no.
Square has different rules.
A square has different rules. By that you mean invariance or something like that.
Yeah.
What's an example?
It has to have all the sides equal.
Has to have all the sides equal. Well, let's think about it. No, we don't have to think about that. That's true. Let's think about if that's a good or a bad thing. When I'm creating a rectangle, presumably I've got something called a constructor that says something like rectangle int width int height. Sorry about the mess. And some constructor here that goes this dot width equals width, this dot height equals height, okay? Now, there's no reason a square couldn't have that constructor, is there? Well, a square could have an extra constructor as well, couldn't it? There's no reason it can't have extra functions. It'd be stupid. Oh, could be.
This would allow it for you to say something was a square, but it wouldn't be a square if you had two different...
Ah, yeah, here's the problem. So Richard's proposed solution number one was, well, why don't we just give square two constructors? One is square which has side, and one is square which has width and height. If we give it both constructors, then I guess it sort of looks the same. But George is saying, what?
If we used the width height one and we gave it two different numbers...
We gave it two different numbers. Yeah, yeah. It's tricky. We could maybe have a rule saying you weren't allowed to do that. How would you enforce that rule? Yeah, yeah, it's sort of looking tricky. I think the problem is that for all the interrogation functions, all the get functions and things like that, a square behaves just like a rectangle. That's what we taught in maths. When you interrogate properties of it, it's got all the things that a rectangle has. It has some additional constraints on it. That's okay, because it satisfies all the rectangle constraints. So if you constructed a square with these additional constraints, it's still going to be a legal rectangle. The problem is if you have a square that can be changed. If you allow your square to be a mutable square, or you allow your rectangle to be a mutable rectangle, then you're in a little bit of trouble, because if you're regarding a square as a rectangle, then it has to have the rectangle changing functions, and presumably the rectangle changing functions include a function to change the width or the height, and then suddenly we can break the square invariant. So yeah, it's a bit tricky. It's a bit of a dilemma, actually, how to actually deal with this problem. Maybe you say there's no relationship between them at all. Maybe you say they're immutable, so that there is a subtyping relationship between them. Let me give you a clear example. Although that's a famous one that perplexes people all the time, people scratch their heads and think, is it a subtype or isn't it a subtype? Certainly is an ISA. My take on that is an immutable square is an immutable rectangle. And a mutable square is not a mutable rectangle. And in maths, when we talk about them, we're just not saying the immutable, but that's what we mean. So our common sense, I think, is still right. The other example I had is, suppose you've got a stack. What we're trying to find here is functions that look like they are subclasses of each other. They support the same functions, but they're not subtypes. You can't use them interchangeably. Suppose we had a stack, and you implemented a stack. It's Adam. No. It is, it's Adam. Adam implements a stack. And what's your name? David implements something called a hopeless stack. And now hopeless stack has, sorry David. Hopeless stack has exactly the same functions as stack. So it looks like they can be used subclassing for each other. It looks like they can be used syntactically substituted for each other. But a hopeless stack, every time you say push something on, it says, yeah, yeah, sure, 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 and it just throws it away. And the stack stays empty forever. And your stack, every time you say put it on, it really puts it on. Can you see syntactically, from the type signatures of the interface functions, it looks like they're the same. You know, from a class on a point of view, from a compiler can check point of view, they look like they can be substituted for each other, but they can't because the semantic contract isn't being fulfilled. Yeah, the meaning of the thing isn't being fulfilled. Now, when we talk about a type, we really think of the meaning. When we're talking about you're a subtype of you, that means you can be used instead of him and everything will still work. And that's vague and wishy-washy, but that's precisely what we mean. And when we say subclassing, we normally mean you implement the same functions he implements, and you implement some more with the same type signatures. But we're saying nothing about the meaning of what's going on, and that's where we can slip up. Okay, so we have this subtle problem that when we talk about, we really shouldn't be interested in subclassing. We really should be interested in subtyping. Though I guess it's interesting, if you have different interface functions, it's clear you can't be subtypes. I mean, we can rule some people out straight away. If they don't have even the functions that you expect, you can't use them for each other. But just having the functions you expect is not enough to let you use two things interchangeably. You also need to have the same meaning, the same invariants held, the same preconditions leading to the same postconditions. Or in fact, you can weaken one and strengthen the other and it'll still work if you're going to substitute one way. Okay, so subtyping is this sort of conceptual idea and subclassing is a sort of syntactical idea. And the principle of subtyping is, the famous one is from the 80s, it's called the Liskov substitution principle. And what that essentially says is if you want something to be a subtype of something else, you have to be able to use it wherever you'd use the something else. Wherever you expect a something else, you should be able to use the original type. If A is a subtype of B, then whenever a function expects a B, you should be able to pass it to an A and everything should still work. And if that works, if that is the case, then you've got a legitimate subtype. And subtypes, as we've pointed out at the top of the page, at the start of the lecture, are a really neat thing when you get to pull them off. But we can see it's not going to be quite as easy as we thought. We're going to be able to easily produce things that look like they're subtypes but aren't. Actually, as programmers, we're going to have to do a lot of work. Yes, Liam?
Just at least with regards to immutable types, if you think of a type as a set of all values that exist in the type, then a subtype is just a subset of those.
That's right, that's right. If it's an immutable one, that's right, that's right. And he said a subtype is a subset if you've got an immutable type. And in the old days, in fact, in non-object-oriented language, we used to do subtyping where we just constrain the range over which something could fall. So you'd have a subtype of the integers would be something that could store all the odd numbers. Yep, that would be a subtype of integer. Yep, that's right. But it's harder to do in Java where functions are more than just returning a value. They're more than just getters. They can do some computation. And to work out if something really is equivalent to something else, to work out if two functions really satisfy some property is, tell me, how hard is it to work out if two functions can be substituted for each other? You could try it and see if it works, and if it didn't work, you'd know straight away. But what if it did work for those particular inputs you tried it on?
You have to have good tests.
You try another one, what's that?
You have good tests.
You have good tests, but what if there's an infinite number of possible inputs you could take in? Or the number of inputs is so big as to be essentially infinite, like you could take a megabyte file of bytes. So it's 265 to the million is the number of possible input cases. It's very hard to exhaustively test that. So exhaustive testing won't tell us if two functions are the same. How do we tell if two functions are the same? We can tell if they're intentionally the same. We can tell if they have the same syntactical code. You remember this from 1927. But to tell if they're extensionally the same, to tell if two functions compute the same function, two syntactical program functions compute the same mathematical function.
All the inputs match all the outputs for both of them.
If all the inputs on both of them matching mean all the outputs on both of them match for all possible sets of all inputs, then they'll be the same. Yes, but how do we tell that? We'll try them all. No, that's what we're talking about. Brute forcing is too many possible inputs. In fact, it turns out it's undecidable. In fact, it turns out you can just substitute the property will halt for one of the properties you're trying to check, and you quickly see this converts into the halting problem. We can't actually do it. Yeah.
I've got a question. What if it's non-deterministic?
What if it's non-deterministic?
The outputs won't match.
Oh yeah, if something's non-deterministic, then they're not classical functions. So you have to have a different notion of equivalence.
So like we couldn't equate Java's RAND to C's RAND?
This is just a very interesting question. The question the Kitten's asked is telling if two functions are equivalent, at least in theory, can be done by brute forcing over all possible inputs, as long as they don't have all possible inputs and there's a bounded number of possible inputs. Bounded range of all possible inputs. But in practice, that's too hard to do because the thing gets explosively big. But even worse is, what if you have functions that are non-deterministic in some way? So for the same inputs don't always produce the same outputs. How can you tell if they're functionally equivalent? And you are describing my PhD thesis, which was given two programs that are concurrent, because concurrent programs are non-deterministic in interesting ways. Their behavior depends not only on the inputs, but also the relative timing of events, which you have no control over. So given two concurrent programs, how can you work out if they're extensionally equivalent? So how can a compiler do optimizations that are provably correct? How can it take serial code you've written and convert it to parallel code and we know that it's all correct? And we don't, 4 years of scratching my head because I couldn't even start. In fact, my whole thesis was about how to start, essentially, because we don't even have a notion of what it means for two concurrent programs to be the same. Oh, we have a million notions. Everyone thinks of a new one every week. So we have no canonical notion of what it even means to be the same. So we don't even know how you could even tell if they were, if you got that, you wouldn't even know that you'd got it, other than waving your hands a bit and saying, oh man, they look the same. I can't think of a reason why they're not the same. So yeah, that's a really hard problem. Okay, but just going back to this, can everyone see? We can check for subclassing. That's a thing a compiler can do. It's mindless. We just look for type signatures and inheritance relationships and things like that. We can see if A and B have a subclass relationship between them, and the compiler will let you substitute them if they are, or Java will let you substitute them if they are, or the Java runtime will let you substitute them if they are. But subtyping, which is what we really care about, that subclassing is just standing as a proxy for, we can't tell. So that's a hard job for us programmers to work out. The compiler has no hope of ever working out. It's actually an intractable problem. It's not an intractable problem, it's an undecidable problem. So it's up to us as programmers to make sure that when we substitute something for something else, we're actually doing something sane. Yet the compiler will never check, will never know that using hopeless stack instead of real stack is a problem. Only we would know that. In that case, it's clear. In some cases, it's much more subtle. Okay, so we've talked about subtyping. We talked about the forgetful stack problem. We talked about mutability. We talked about not being decidable. Okay. Whew. Now, let's just take a quick break for 10 seconds. Can someone think of some sort of thing we could say that would be interesting for 10 seconds and then we could go back to really hard work but yet would feel relaxed and refreshed? What's everyone's favourite movie? Who likes Avatar? Cool. But do you still think James Cameron would have been better if he'd spent $1 million getting someone else to write the script? Yes, because the effects were fantastic. What did you like about it? The effects were fantastic. The values were beautiful. The world was fantastic. The sad things were incredibly sad. Jumping on when he was flying on the thing, it's just you go, oh, yeah. Has anyone read Death World by Harry Harrison? Oh, you should all read it. In the old days when science fiction books were just that fat, but they contained as much story as Harry Potter, a man called Harry Harrison wrote Death World. Excellent, excellent book, which James Cameron appears to have ripped off. Okay, is everyone now refreshed or should we do something else? Have a break? No, we can't have a break. There's no time for rest. There's no time for fun. There's no time for games. Okay, I do have something to show you. Why don't we have this we're going to have a little break soon. I'll show you one little refresher now. I'm going to talk about pouring a beer. Here we go, let's turn down the lights. When we talk about OO, design, as we start, you see we're getting to an interesting part in the course now, stamps his foot, because now you know enough Java syntax that actually when we give you a problem, instead of it just being like in C, or well, not even in C, but instead of it being like in the early days where you go, oh, there's only one way to do this, I'll just do it now. Hopefully now, whenever you see a problem, you think, oh, there's 60 million things I could do to solve this. There's 20,000 different ways I could go. How can I even assess which is the best one? How can I tell which is a good design and which is a bad design? Like when the architects were told, design an opera house for Sydney, they had so many choices, it was very hard, they were sort of paralysed. How can you actually come up with something good? How can you make sure you don't come up with a sterance? So we have a couple of good ideas. One is, the OO idea is, well, let's try and model it. Let's make the solution model the problem as closely as we can. That can be a good idea to sort of stop us introducing extra complexity in the problem that doesn't even have to be there. Then the keep it simple, stupid philosophy is one that we passionately believe in this course, which is at any given instant, just write the simplest thing that works. And I don't want you thinking, I'll do something a bit more elaborate, although I don't need it now, it might help me tomorrow or next week. No, don't do that. For example, the example that's most forefront of my mind now is design task 2, which we told you 3 wheels and we gave them names, front, middle and rear. And it would have been very tempting, I nearly did it myself, to think, oh, I'm just going to store 3 wheels in my class. And then you think, no, hang on, 3, that's a bit arbitrary, isn't it? I should probably have an array of wheels. I should have a constant somewhere that tells me how many wheels I've got. I should be able to iterate over it. And that way, if I ever want to make the lock work on more than 3 wheels, I'll just have to change this one little constant at the top and everything will work. So I'll just make this more complex thing that I don't need now because later on, this will save me time. I would have done that. I would have had to bite my hands to stop myself doing that, but don't do that. We don't want to do that. If the thing needs 3 and it's given them 3 names, put 3 in your solution, give them 3 names. Later on, if you need 4, rewrite it then to put 4 in. Later on, if you need it to be 5, start to think, I'm needing to change this all the time, it needs to be an array. But don't do it now, do it when you need it. Yes?
I got told off for writing in 3 names.
Who told you that?
My tutor.
What names were they?
I had rear wheel,
Rear?
mid wheel,
Mid?
front wheel.
Your names match the spec?
Yeah.
And your tutor told you off?
Yeah, so I used an array.
You should have used an array because that's more general. That's what we all think, isn't it? That's certainly our approach would be in C or anything else. You think, I'll write this big elaborate structure, a bit of investigation up front, a bit of extra work up front will make everything work better later on. But actually what we've seen is a little bit of extra work up front turns into a lot of extra work up front and turns into a huge amount of extra work up front, and then we have Duke Nukem forever. What we want is we want you to ship the thing and we want it to work and we want it to meet the constraints, and that's all you have to do. And if you want to put extra things in, do them on your own time when the whole thing's over. Write beautiful, fantastic code, but don't make it more general than it has to be, even though that hurts us all. We all know that's the right thing to do. Don't do it, because if you ever need it to be more flexible, how long would it take to change it to an array?
Not very long.
3 seconds with your partner sitting next to you, using the refactor facilities that come with Eclipse and Agile Programming. So the whole idea of Agile Programming is you just write what you need now. Don't try and anticipate problems, because there's too many and you'll just spend all your time anticipating. Write literally just what you need now, and later on, if you need something else, it's very easy to put it in because you've built up a bank of unit tests that can be automated. You've got tools for refactoring, and the Agile method is you just stick it in when you need it, if you need it. Does that make sense? So you go to your tutor and say, just cry. Just cry. Say, oh man, Richard's crossing me in lectures, you're crossing me in the tutes. So here's an example of someone who didn't do the simplest thing that they could do. And then we're going straight after this into the part 1B of the lecture. This is a Rube Goldberg machine. We need more sound. Maybe there is no sound. He's just going around showing us the whole machine. We don't even need to see it. Let's just see it when it goes. Here comes. Yeah, right. He's about to put the beer can on the lever. Oh, that's going to set the metronome going. How about that? That deserves a hand. Okay, Rube Goldberg machines are famous machines to solve something in the most complicated way you possibly can. Okay, that's not what we're going to do in this course. Now, I hope you've all had a refreshing break. It's really nice to see you. Have you all had a nice holiday? Did anyone do anything good? Fantastic. You saw some movies, poured some beer, watched someone else pour a beer. Feeling thirsty. Let's now go back to the second part of the lecture. Okay. I want to check that everyone understands basic Java syntax. So I've just made a link to the Java basic syntax trail. So click on that and just follow that tute, just to check you can do everything about Java that's in that tute. Oh, sorry, let me turn off the lines. That work? Yep, click on that to follow the tute. Java has both primitive types and classes. And it was a funny design decision. In a perfect OO language, everything is an object and belongs to a class. But for efficiency and speed and various other reasons, they made an early decision in Java that they would still support primitive types like integers and chars and things like that, as well as having classes. So it does give us a little bit of complexity, as you've seen, because when you pass an integer around, assign an integer, it's done by copy. When you assign an object, it's done by reference. When you compare them, objects, you're comparing references. When you compare primitive classes, you're comparing for value equality. The primitive types, I just got a link here because I want you to know all the primitive types, because one came up in this week's tute and you might not have known it, which was byte. Here are all the numeric types. There's byte, which is just 8 bits, short, which is 16 bits, int, which is 32 bits, long, which is 64 bits, float, double, and boolean, and char. Now they're all familiar except for boolean from C, but the difference between Java and C is in C, to be flexible, C never specifies how many bits each of these types have. The idea being then you could write your code and it could run on lots of different machines. But it turned out that was a nasty mistake. And it turned out to be a pain because people started implicitly assuming each type was a certain length. And then when you moved your code to another type and just changed the size of ints on that, suddenly a whole other code didn't work. Although syntactically it worked, the semantic contract started to fail. So Java, they decided, well, let's not even try for that flexibility. Let's just be honest and upfront and blunt about it and say an int is 32, is 32, is 32, is 32. And that's all there is, and it's signed. No such thing as unsigned. And a long is 64, is 64, is 64. And I guess as machines get bigger and bigger and bigger over time, maybe Java's types are going to need to be augmented with even bigger types. Maybe they're not going to be able to move forward like C types can, but hopefully the advantage is you're not going to get subtle memory use problems because you're using what you think is a 32-bit number, but it's really only a 16-bit number on a particular machine. Okay, so just read through that and make sure you know all the basic types. The primitive types. Now, I wanted to talk about Java documentation. The design task you're doing now, design task 3, is a funny one. In the first design task, we really were just testing 1927 stuff, making sure you knew how to think like a scientist and do an analysis. In the second design task, we wanted to check that you understood the idea of object orientation was modeling, and we gave you something to model, like locks with wheels, and we wanted to make sure you created a lock class and wheel class and you set the relationships right between them. And whether you did or not, hopefully at the end of the exercise, it all makes sense to you. The third one now doesn't really seem to involve objects or classes much at all. It involves getting a sound file and reversing it. And the effect I really want you to get is the Buckaroo Banzai effect. You know Buckaroo Banzai, the world's best movie ever made, where they make the alien voices, I understand. I can't actually find it anywhere on the internet now, but maybe I dreamed it. But I believe how they made the alien voices was the aliens would say whatever they wanted to say, like, what's something the aliens say in Buckaroo Banzai? They say all these amazing things. I wish I could remember a John quote. Does anyone remember a single Buckaroo Banzai quote? Monkey boy. This is not my planet, monkey boy, one of them says to one of the humans. So how he does it is he says, this is not my planet, monkey boy, and they record it. Then they play it backwards. And it sounds like, then they record that and play it backwards. And that's how they get the alien voices. So you practice speaking backwards and then you record it and play it backwards. So I was hoping you guys could do some Buckaroo Banzai stuff for your challenge things and say some dialogue and then practice saying it backwards and then record it backwards, if that makes sense, to make it go forwards, but it sounds weird because it's backwards. Does that make sense? It doesn't really make sense, does it? And the other thing I'd quite like you to do is see if you can record things that when you play them forwards and backwards, they both make sense. Because I've been listening to a lot of the backmask songs and it's sort of obvious there's backmasking there because you hear this, but it'd be really nice if it said something like, I love the Queen, but when you played it backwards, it said something like, haha, I don't really love the Queen. You know, or I'm not being disrespectful to the Queen. Insert your monarch or tyrant of choice. So I'd quite like it if you could do any of those things for brownie points, not for any marks at all. So the exercise is to write something that makes sound go backwards. And why is that an interesting task? It's interesting for two reasons. One, because it demonstrates that no matter how much you prepare for something, you'll always stuff it up. Because although we prepared massively for it, we never thought to check that the machines in the labs actually could play sounds. And this is a good hint for you if you're doing a design presentation at any time soon, because you can be sure when you turn up to do your design presentation that the overhead projector won't work, that you'll have dropped your sheets on the ground and water will have wet all the water, and that everyone will turn up late, and that everything that could possibly go wrong will go wrong. And you have to design your talk so that in spite of everything failing, you're still able to give the talk. So make sure you've got spare copies of overheads, make sure you're not relying on any piece of technology working because it won't, and all that sort of stuff. I want you to be really defensive, and I deliberately did this incredible stuff up with Silent Labs just to do that. So how are you going to debug it? How I was debugging it to make sure it worked was I actually got a bit editor, opened it up and looked at the files byte by bytes and checked that they were reversing the bytes. Well, it wasn't much fun. Someone suggested you could reverse it twice and check you got the original sound file back. But then I thought someone could write hopeless stack. Okay. So lots of things you can do. I suggest everyone bring a laptop along to the lab so you can get the joy of reverse sound. Yes? Which one? Audacity's on all computers. Yeah, but I don't think they have speakers.
No, but it means you can view the sound file.
Oh, you can view the sound file. Oh, yeah. Yes. You can check the envelope looks reversed and things. Oh, you can? Oh, okay. I didn't know that. Oh, good. Okay. Kitten just pointed out that Audacity lets you reverse it yourself. So you could load it into Audacity, reverse it, save it out as a WAV file, and then just do a file compare to see if they're the same. But is that as exciting as playing it backwards like I was doing to my kids the other day, making sure I picked the right ones to play backwards? Yes. No, I like hearing the sound. It just made me giggle and giggle and giggle. Okay, so what we're talking about there. Documentation. So the reason we set this task for you is I wanted you to learn something important about Java, which is that Java is simultaneously good and horrible. It has 1 million libraries with 1 million functions that can do everything, which is fantastic. But the horrible thing is there are 1 million libraries with 1 million functions that can do everything, which is depressing because now you think, how do I do this? I'll just start at 1, 2, 3, 4, 5, 6. So you've got to do a lot of reading and a lot of browsing of documentation. So I thought, why don't I show you how Java documentation works? So here's what I do. You can download it and store it locally. I never remember to do that. It's probably a really good thing to do. So I just use Google. I say Java documentation. Hang on, let me open another window because I had some examples I wanted to look up. Let's go File, New Window. Here we are. Oh, there's a Google window there already. Let's just move that down. Okay, got it. Right, so what do I want to see? I wanted to look up, say, java.lang.integer. Okay, let's look up java.lang.integer. So we Google Java documentation. Oh, good, 1.6. I always seem to end up with documentation 1.4 or something crazy. Here we are, Java 6 documentation. Let's just click it. You can store it locally, but it looks like this. Has everyone seen this sort of thing already? Have you been poking around in this, feeling a bit depressed because it goes on forever? Here are all the classes that are documented here. I understand there's, does anyone know the numbers? I was going to say hundreds of classes and thousands of functions, but it might be thousands of classes and Googles of function or something like that. It's an enormous lot of them. So let's suppose we want to look up the integer class. Now I told you that Java had primitive types as well as having basic types. The basic types are primitive types. So it stores a number, literally just stored as a number. It's not an object. So an integer in Java is just a primitive thing. It's not a class. It's not an object. It's not a member of a class. But actually, Java sort of did it both ways. They said, although our integers are called ints and they're just primitive things, let's also make a class called integer. Man, that's a great idea. Because why is it a great idea? It's a great idea for this reason. At some point, we're going to want some functions that can work on integers. And those sort of functions in the object-oriented way of thinking should really be attached to the integers. They should belong to the integer class or the integer object. But unfortunately, our integers are primitive types, so they can't have things attached to them. But there's nowhere else in Java to put them. The only place you can put functions is attaching them to some object. So where are we going to put all the functions about integers? And I thought, well, we'll make a mock integer class, a boxed up integer, and we'll call it capital I integer, and we'll put all our functions in there. So let's look down here. And if you were really excited, that's A, B. If you're really excited, you can actually store even numbers in the integer class, and you can make integer objects if you really wanted to. But let's keep all our objects primitive, but let's use the integer class functions. I, J, I'm going the wrong way, aren't I? Thank you, not good with the alphabet. Integer, here we go. Boom. So let's look up the integer class. Let's make it a bit bigger for you. Here we go. Class is called integer. Now, this is the important thing. Oh, not the important thing. Here's an interesting thing. At the top, it tells us the subclass relationship in the Java hierarchy tree sort of thing. It's saying, look, if you're an integer, that's a subclass of the class called number, which means that anything that expects a number could take an integer. But anything expects an integer, can it take a number? No, unless the subclassing goes both ways. And all numbers are examples of objects. And in fact, Java has a class called object. And everything in every single object you'll ever make is a subclass of object. Which means that every single thing you'll ever make, any object you'll ever make, has all the methods that object has. You just don't know it. Java sticks them in for you automatically. Do you want to see what object can do? Let's just click on it. Objects. What do you get with objects? You get equals and clone. Remember I told you, you always get equals and clone. You get finalized, don't worry about that. Hash code, we'll look at that later. Notify, notify, notify. To string is an interesting one. Every object automatically can be converted to a string if it needs to be. So if you convert a number to a string, it just converts it to the digits in the normal way. If you convert a string to a string, it's just itself. But if you make any other objects, like you've made a lock or something like that, call .toString on it and print that out with system.out.println and see what it looks like when it converts it to a string. Every object can be converted to a string. And there's not many others. All the rest are sort of to do with concurrency, really. Okay. These are some interfaces that integer implements. Serializable, comparable. Worry about that later on. All right, then there's some words explaining what an integer is. Blah, 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 worth reading. Blah, 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 blah. That book is worth reading. Hacker's delight. Here are the constants. Here are the fields that it has. The constant fields, static int, max value, static int, min value. So you want to get the maximum and minimum integers. You'd go integer dot max value. Yeah, that'll give it to you. Its size, the number of bits they use to represent it. Here's a constructor for making one if you ever needed to make one of these integer objects. You see you can just make it from an integer. But here are all the methods. That's what I wanted to show you. Bit count tells you how many bits are in it. Byte converts it to a byte. Byte value, sorry. Converts it to a byte. Compare two integers together. There's a compare to function. Decode, that's a neat one. If someone ever gives you a string that represents an integer and you want to convert it to an integer, so it's like quote, quote, 42, quote, quote, and you want to make that a string, just call it, what was it called? I've lost it, where is it? Decode? Decode. And hundreds of other interesting functions. You can do all sorts of things, trailing integers, parse it. Oh yeah, convert strings to integers in a different radix, so you can change the base. Convert it to a short, rotate the bits on it, convert it to a binary string, convert it to a hex string, convert it to a normal string, find the value of a string. Okay, and then all this details about all those functions. Woo, a lot of stuff about integer. So how did I find it? I either downloaded the Java doco myself and it's on my computer and I found it that way, or I just Googled Java documentation and I find it. And the Java stuff, although there's a million of them, the nice thing is it's all documented in a fairly beautiful way like this. Now let's go back to packages. In C, we have libraries. Libraries are like where you put a whole lot of useful things that people might need and you sort of keep them together in one bit. So rather than having to import millions and millions of things into your C program, hash include millions of things, they're squished together into a sort of common unit and you hash include that unit and you get all that stuff. So you hash include std.io, you get all the IO stuff. You hash include assert, you get everything you need to do with asserts. It's a good idea. Java does a similar thing. Common things in Java tend to be lumped together into something called a package. And next week, or maybe the week after, we'll see how to make packages ourselves. At the moment, we don't say anything, so we're all going into something called the default package. If you want to use something, you actually always have to say what package it's in. So if I wanted to talk about a string, which it starts with capital S, that's actually defined in the package called java.lang. And package names always start with lowercase letters, by the way. That's a convention. So java.lang.string is what I should say. So I shouldn't say string name when I'm declaring a string. I should really say java.lang.string name. But who wants to say that? No one. So what Java does is the Java system, and that's just to specifically say which sort of string I'm talking about. Because you might have written a string object, a string class in your package, and you might have written a string class in your package, and you might have written a string class in your package, and there's a string class in java.lang, and I need to know which of those strings my program's using, because they're all available sitting there for my program to use. So you say the package name dot whatever class you want, and that gets you that specific one. But Java has a rule that if you leave off the package name, it does a bit of sensible searching to find it. And it always searches in java.lang. So all the standard stuff that's in java.lang, you never actually have to say, you never explicitly say where it's come from. Let's look at java.lang. We've got that other file here somewhere, don't we? Java. Let's, top. It's up here, isn't it? Packages. Oh, here. Oh, it's down. It's not showing. Let's look at all the packages. At the moment, it's showing all packages down here. The list of classes down here is enormous because it's showing me all possible packages. But I can say, just show me one package, java.lang. Here we are. Now it's just showing me all the stuff in java.lang. Or Boolean. Have you ever used that? No, you've never used these. These are the big ones that mock up. These box up the primitive types. But here's some things you've used. Integer we just looked at. Oh, have we used math before? Have you ever used math? Java.lang.math. I might have told you to use math.random if you wanted to get a random number. Yeah, math is a cool class that has lots of mathematical functions in it. Oh, everything's an object. The object class is defined in java.lang, java.lang.object. Everything's a Java. Does it say that at the top? When we looked at a class before? Let's look at integer. It said, yeah, it says, look, it says java.lang.object. It is a java.lang.object. Okay, good. Whew. Okay, so java.lang, you could just browse through it and look at all the interesting things in java.lang, and they're the things you never need to give a fully qualified name for. So basically everything you've been talking about so far is either something you've defined yourself, which is in the default package, and you don't have to give a package name for that, or it's in java.lang and you don't have to give a name. But if you want anything else, you're going to have to say the package name. So if you want to get something fancy from java.io, you're going to have to say java.io. Whatever you want. And as you can imagine, that gets a bit annoying if you do the same thing over and over again. So Java has a facility called importing. But it's not like the C's hash including. In C, when you hash include something, it all just gets embedded in your code, right? It all just gets, you get that whole library just compiled in. Importing actually doesn't move anything in. It just sort of adds to the list of places where it'll search to look for stuff. So if you said import java.io.star, star means everything, that means everything from java.io can now be used without you having to say java.io.star. Does that make sense? Okay. Whew. So now you've seen about packages, and I've showed you .integer, and I've shown you math, and I wanted to show you some stuff in string, and then I wanted to show you java.util.scanner. All right, let's look at java. Now, where's string going to be defined? What package would that be in? Java.lang. That's right. So are we already on java.lang? Yep. So let's go down and look at what a string looks like, the string class. It's a very interesting class. I was talking a lot about strings yesterday, and I was talking about how you compare them and how it's tricky where you're comparing them by value or by comparing pointers, and we talked about various things like that. And someone came up to me afterwards and said, this thing that Java does of making sure that all literals are all stored in the one spot, in the same spot, so it doesn't ever store two different copies of the same literal value, that must be very hard to do if people are changing string values all the time, which I thought was a very good observation. And it reminded me that I forgot to tell you that in Java, you can never change string values. Strings are immutable. So if you've got a string and you want to add some letters to it, you make a new string by getting that string plus some extra letters on the end. So you never ever change strings, we just make new ones all the time. And to join strings together, because it's a bit of a pain to do that with operations, with named functions, Java has a nice bit of shorthand, which is plus, the plus symbol, the plus operator, as well as doing addition, if given two numeric values, does string concatenation if given two strings. So if I said system.out.println hi plus 6 plus free man, this will print out hi 6 free man, automatically capitalizing the F. Does that make sense? Plus actually joins the two things together. It also has this, C also does this other, Java also does this other nice thing, which is if you've got some, if I did this, hi plus free man, that makes sense that plus is concatenating two strings and giving a string. But if I said hi plus 6 plus free man, actually it's a bit more subtle what's going on here, isn't it? Depending on whether it's working from left to right or right to left, let's suppose it works from left to right, so it brackets it like this. It first of all converts 6 to a string, and then it concatenates it on, and then it gets that string and concatenates freeman to the end of it. How does it convert 6 to a string? It calls a toString function. So in fact, you could stick any object in here. It doesn't just have to be a number. And if you're trying to print it out, Java will convert it to a string automatically using toString, which every object has. So that's pretty cool, isn't it? Yeah. Okay. Does anyone want to ask a question about that? Every object has a toString function which converts that object to a string, sometimes in a fairly lame way. And whenever you use plus, Java concatenates two strings together. And if you're giving it something that's not a string, when it's expecting a string, it'll automatically, behind the scenes, run toString on it for you to convert it into a string. Okay, and the last thing I wanted to show you was java.util.scanner. Now, where's that going to be? I could look for java.util down here, open that package, and then we could find scanner. Yeah, that's probably the way to go. Or I could have just gone to the top and said, show me all packages, all classes, and all classes in all packages, and then I'd have had to scroll further down here, because it would have been a ridiculously long list. Let's look for scanner, the class scanner. Java.util.scanner. Here we are. This is a nice class. What's it a subclass of? Object, right? Has nothing else above it in the hierarchy. So if something's expecting an object, you could pass it a scanner, but other than that, you can only give it to things that are expecting a scanner. You make a scanner with the new scanner function, of course. It's got a constructor that makes it. And once you've got a scanner, scanners are really good at doing what? Those that have already been itching for me to tell everyone how to use them. Parsing. Given a string, they're good at breaking it into bits and extracting things out of it. So if someone gives you a long string of arguments, say, the command line arguments to your function, and you want to strip them down and pull minuses out and convert characters to numbers and do all sorts of things, the scanner class here, awesome, has all sorts of amazing functions that will let you change strings as much as you want. They're very good. So we've now done java.util.scanner. Have we done java.util? Yes, but I don't want you to use any of the collections. I don't want at the moment to see any of the collections like dictionary, enum, any of the map functions, anything like that. But I'll assume that you can poke around in java.util and you'll just look for interesting things to look at. And I'll certainly point out anytime I think you need to know something that it's in that class. Okay, so I think we've done all the catch-up stuff I wanted to do. Oh no, one last thing, and then we're there. And then we can have our real break. Documentation. You've got to submit your code and you've got to talk about your design. And I bet you went to a lot of trouble to try and document what your classes look like and what methods there were and how they related to other classes and the interface inheritance relationships and things like that. And it's a real pain in the bum, and I bet you did all this typesetting and formatting. And I bet if you got it right now, as you keep changing your project, it'll be wrong and you'll have to keep updating that thing. And it'll be really annoying because you have to change your source code and then you have to go and change the documentation. Change your source code, change your pretty pictures, change the source, and you'll never get it quite right, and this will always be a bit out of date and not quite synchronized up. And this is the eternal bane of documentation, is we have a strong incentive to get the code right, but we don't have a strong incentive to get the documentation right. And if the code's wrong, we look like an idiot. If the documentation's wrong, we look like an idiot to a much smaller group of people. And much, much later in time, not till they look at it. So we can probably get away with it. So, because we're always in a rush, we're naturally inclined to not do the documentation properly. So all these very clever computer scientists have thought of a whole range of things of encouraging people to write better documentation, setting the mechanisms up so you actually have an incentive to get it right. One really clever thing from Knuth is called Literate Programming, where your programs are actually a document themselves. And the cool thing about literate programming is every line is a comment unless you say it's not. So you just write your story, you write an essay, and then suddenly you put a special character in, which means, oh, and here's a line of program now, and your program is scattered through your actual document. And the document is the center. Yeah, it's quite amazing, isn't it? And people have tried all sorts of other things to keep the code in sync with the doco, including some extreme people who say, well, let's not have any doco at all, my code self-documents itself, which always impresses me and depresses me simultaneously. It impresses me because it is such a noble aim to make your code document itself. And I think that is the perfect program. And if you wrote a program that needed no documentation, you are the world's best program, and that's fantastic. But depressing in that every time someone does that, I always disagree with them. So I think, you think it's fantastic, and it is really good, but not putting you particularly, Jared, or at all, Jared. I'm pointing to that empty chair there. But we're always over-optimistic about how clear our program is, because at the instant of writing it, we actually understand it reasonably well ourselves. So it's a noble aim to not document your programs. And were you able to pull it off and have a program that didn't need it, you would be amazing. But I suggest you apply skepticism and just assume that you're not going to be able to pull it off. So do stick some documentation in. So Sun, Java, the Java idea of how to make our doco not too painful to get right and keep up to date is Java wrote a tool called, Sun wrote a tool called Java Doc. And it comes with Java C and the Java thing and the jar and all those other binaries you get in the JVC. And the JVC, that's a hi-fi shop, isn't it? JDK, thank you. All the things you get in the all the things you get in the JDK. You also get JavaDoc, and JavaDoc's a tool. You put it in the directory, you put all your source code in, and you say JavaDoc minus public. I'm just interested in the public stuff. star.java. Go! And you hit enter, and then it does this. I have a printout of it here. I did it just before I came in. It does this. I got my lock code, and I said JavaDoc negative public star.java, and it did all this. It went, and then it finished. And it creates a beautiful network collection of HTML pages that fully document everything that's going on, that look exactly like the Sun Java documentation we've been browsing through. In fact, all that Sun Java documentation we've been browsing through was generated by JavaDoc. And so here's an example. If you want to put some JavaDoc makes a reasonable guess at it anyway, but you can give it extra information. If you start a comment with slash star, that means this is a comment that will actually get embedded in the JavaDoc. This is quite a long comment. I don't know that you'd write such a big one. You can put HTML in here. It'll get formatted as HTML, which raises an interesting security problem. Look at this. The first sentence is very important. That'll be printed bold and in the summary. Then the rest is a summary of the whole thing. And then if you start something with an ampersand, it has a special meaning. So ampersand param means I'm about to describe the parameters that go into it. URL is an absolute URL, blah, 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 blah. Describes the return value. And there's an also C. Also, you might want to check out the image class. So you type that goop in, and this is what it produces when you run JavaDoc on it. Page that looks like this. Beautiful page with links you can click on. And you can click on here, and it takes you to any of the other classes that it's linked to. It prints your summary. It talks about the class name, and it gives you all the parameters and everything. And it's just absolutely fantastic. So with no pain at all, as you type your code, you just write a few JavaDoc comments in there. And then when it comes time to do your presentation, you go JavaDoc, negative public, star.java, boom, and your whole presentation's there. Fantastic, done for you. And it's awesome to be able to view through your code. Because as I've pointed out several times now, both the interesting and wonder of Java programs, but the depressing pain of Java programs is you end up with a million fairly small objects interacting with each other, and a million small classes describing that interaction. And that's really neat way of dealing with the problem, but also incredibly messy, because now you've got a million files, but they're all brought together by JavaDoc. So you can keep track of what you're doing. Whew, that's all I wanted to say to catch up. And now we're going to have a real break before we return for the second half of the lecture. So the real break will go for, I would say 5 minutes, but that doesn't sound very long. So we've got 300 seconds.